Here we go. So today we're going to begin looking at one of the last, this is the last section of chapter 4 that we're going to study. There is one more section of chapter 4 in the textbook. I decided not to get into it. We're just going to do 4.4 and then we're going to stop. Second to last day before spring break, folks. So we're going to wrap up chapter 4 this week so that when we come back from spring break, we can start a clean, fresh, new subject. Okay. This section is on something called the logistic equation. It's very important. It's a specific, very important differential equation with applications in biology, social sciences, economics, political science, that sort of thing. Not so much physics and engineering, more so the social sciences and biology. But it's a great application. It's a great example of a differential equation with some cool properties. And it's separable, so we can solve it. And so we're going to study it. We're going to mainly approach this, this equation from the perspective of population growth. So let's talk population growth. First, the naive model that we have looked at before. So how have we talked about population growth in the past? We've said, hey, as the number of rabbits increases, the rate at which the population grows also increases. And before, we looked at this differential equation, that p prime is a multiple of p. Basically, that the rate of growth is proportional to the population itself, right? When you solve this differential equation, as we have in the past, we got some constant multiple of e to the power kt, which means that we're talking about growth that looks like this. It starts at some initial population value, and it goes up, and it grows exponentially over time. This has an obvious flaw, which is that population does not grow without bound. Right? It does not go to infinity over time. And so the reason for that, the reason it doesn't grow to infinity is because within an environment, there is usually some limitation on resources, or maybe there are predators or something. And if the population grows very large, then that strains the resources available in the environment. And then fewer of those members of the population will survive, and therefore that will put a damper on the population. Okay, so there's a term used in biology Here's a more sophisticated model, okay? And it's going to incorporate a thing called a carrying capacity. That's the term I was referring to. This is going to be sort of like the maximum population that the environment can sustain. And we're going to figure out what exactly that differential equation should look like. But what the graph should look like is something like this. You have some starting population. Here's your starting population. Maybe it's small. But then you have your carrying capacity, the maximum population. The textbook calls this capital K, which I find slightly annoying because we were using lowercase k for the constant of proportionality. in this section, oh, I forgot. In this section, the textbook does a little flippity flop, and it uses the letter R. They just, I don't know, they just turned the tables on us, and they decided to use the letter R for that constant of proportionality instead of K. R is a very reasonable letter to use for it because it is the exponential growth rate, and so since it's sort of a growth rate, it's R, a rate. I don't know, it makes sense. But anyway, we're gonna change our notation to be in keeping with the book, just so that you don't get confused when you look at the textbook. So carrying capacity, we use the letter K. K for carrying capacity. I know, I'm sorry. But we're going to use K for carrying capacity. And so the idea here is that the population can't get bigger than that. If the population ever did end up bigger than that, it would end up trending back down towards that carrying capacity. What happens if the population is smaller is that it starts increasing. It starts roughly exponentially. So it looks like that exponential growth, but after a while, there's going to be an inflection point, and it's going to level off and approach K asymptotically. Okay, and that's what we should expect the population to do. Okay. By the way, y equals K is a stable equilibrium solution. For this differential equation. I haven't even written down yet. We haven't gotten to the differential equation. We'll get to that in a minute. But y equals K is going to be a stable equilibrium solution for it. If you ever have exactly K members of the population, that's going to be a stable. Like if you go away from K, if you have more or less, it's going to trend back to K very quickly, because K is exactly the amount where the environment is stable and the resources in the environment can sustain exactly that many. So the population should stay at K. It should be constant. Okay, this is the way we model it. What should that differential equation look like? Well, you want it to sort of still encompass this idea, right? This exponential growth idea that as the population grows, the rate of growth is proportional to that population. You want it to still encompass that idea, but not only be reliant on that one idea. It's kind of like we're going to take the two ideas of exponential growth rate and carrying capacity and combine them together, okay? And here's how you do it. You say, let's have P prime, let's have that be not just proportional to the population, but jointly proportional to the growing population and also the shrinking sort of distance from the carrying capacity. So that way it's proportional to the population. So as the population grows, it's going to grow faster. But as we get closer and closer to that carrying capacity, right? This is that distance away from the carrying capacity. As we get closer to that carrying capacity, it's also proportional to that, right? And that distance, that distance away from the carrying capacity is shrinking. So that's going to have a diminishing effect on the rate of growth. It's going to slow us down, all right? So by making it jointly proportional to basically this distance, which is getting bigger, right? But also this distance, which is getting smaller, right? Then when it's far away, from the carrying capacity, it's going to act more like exponential growth. And as it gets closer to carrying capacity, it's going to end up acting more like it's going to start leveling off. Okay. Because that thing which is close to zero is going to be more dominant. Okay, so there's a little bit of a caveat here, which is actually the distance from carrying capacity is represented as a percent. Okay. So so the way that what the differential equation actually ends up looking like is I'll show you. Let's compress all this. Wow, I have a lot of different layers here. Oh wait, no, what am I doing? Oh no. I just did the opposite of what I meant to do. I need to compress it down. There we go. Right. Take all that, make it a bit smaller. Here's what it looks like. We have P prime. It's going to equal to it's proportional to P. So it starts out looking just like the original one, right? P prime equals RP, except it's also proportional to like P minus, or sorry, not P, it's K minus P. The distance away from that, like that's the distance away, right? Let me color code this. So P is our population, that's in blue right here. And then the distance away from the distance away from the carrying capacity is K minus P. But like I said, we're actually going to do that as a percentage. So we're going to divide that by its percent of K. So actually divide that by K like that. Okay. So if you distribute that division by K, you get the traditional version of this equation. We'll write just beneath it. P prime equals RP times 1 minus P over K. Like that. That's how you usually see the logistic equation written. And that is what this is, my friends. This is called the logistic equation. Okay. It is a differential equation whose solutions are going to look like this. They're going to have this sort of carrying capacity built into them, right? It's like it's combination of exponential growth and also carrying capacity. Okay. And then if we want to adjust things about it, we just have to adjust the parameters like R and P and K and stuff. R and K, sorry, P is the solution. P is like the variable, but R and K would be parameters we can adjust. So let's have a look at this sort of thing over in our little thing that I sent you guys yesterday. There we go. It's our little slope field plotter. Sorry, my computer's being slow again. Come on, computer Dora. You can do it. All I'm trying to do is move a window. Really? I'm just saying why it won't just. Okay, well, I don't know. For some reason, I was trying to grab just that tab and move that tab. Usually, if you grab the tab, you can pull it away, but it won't do that. Whatever. All right. So Y is P. All right. We want like, remember, it's like RP times 1 minus P over K. That's what we want it to look like, right? Except let's put in a value for R. Let's put in R equals like 0.5. And then let's put in a carrying capacity of like 3. All right. So now we have this sort of exponential growth rate of 0.5, but a carrying capacity of 3. So as you can see, if I look at my different solutions here, if I kind of move this initial value around, you can see my solutions have the carrying capacity of 3, right? They head up there towards 3. And the 0.5 is sort of a measure of how fast this exponential growth rate happens at the beginning, at least. If I increase that to something large, like let's make it 5. If I make r equal to 5, then we have this very fast exponential growth at the beginning. And you can really see it. And you can really see that carrying capacity on the right. And as you can see, if I think, like I mentioned this earlier, if the population ends up higher than the carrying capacity, then the solutions to this model show the population diminishing back towards the carrying capacity. You can also bring your population negative, but that obviously isn't really, that doesn't have a real world meaning. We don't have negative population, so this doesn't really mean anything in the context of population. But if you're curious, if you end up with if you bring your initial value down here, it goes down to negative infinity. It's because this is a unstable equilibrium at 0 and a stable equilibrium at the carrying capacity up at the top 3 in our case. So yeah, there's a picture of what it looks like. So now, in order for us to figure out what is a formula for this curve, this sort of S-shaped curve, we would like to know what that function is, right? So that we can do things with it. So let's get back over to our whiteboard and solve the differential equation. Okay. Isn't this cool that you can set up a differential equation to have solutions that look the way you want them to before you even know what the formula is? Isn't that cool? Yeah. A lot of applied mathematics is about differential equations. And back in, I'm just gonna go on a little rant, not a rant, a tangent for a moment. Back in like college algebra, when you're studying like functions, and you first start studying functions and you start talking about, yeah, functions are used to describe real world scenarios, you know? Students will sometimes ask, well, like, how do people actually find the function that describes that thing? And sometimes back in pre-calculus or college algebra, the best you can say is like, well, have you ever taken a statistics class? Have you done linear regression or polynomial regression? Because like, that's one way that people find it. It's like they look at a data set and they do some sort of curve of best fit. And then that's one way that they can find a function to describe something. But another way to do it is through differential equations, where you look at the rates involved and you make some sort of broad assumptions about how things work, and you come up with a model that has the properties you want it to have. You get a differential equation that describes that, and then you solve the differential equation to find the formula for the function. That's what we're doing here. Anyway, I just wanted to put that context out there because I think that it kind of nicely frames or ties back into the stuff that you guys studied back in the day. Okay, so now let's solve this. P prime is r times p times 1 minus p over k. We're just going to go ahead and keep the r and the k as like arbitrary. Like, we're not going to specify what they are right now. We're going to treat them as constants while we're working. R and k are constants. So when we're done, we'll have an answer which is incorporating, which we can change the value of those parameters to be whatever we want them to be. P is a variable and T is a variable. Let's rewrite this so that it's clear what variables we're working with. P is the function, P is the population changing over time. That's the variable, like the output variable. And the input variable is time. So pretty much all of this, we're going to want to move it over to that side. and then dt will move it over to this side. So we're going to do like 1 over p times 1 minus p over k. All of that involves p. And then on the right side, all we have is r, just r dt. Now we're going to integrate both sides, right? We've sort of separated, now we're going to integrate. But actually, before we integrate, there's a couple of steps that we can do to make the left side easier to integrate. So first of all, I'm going to get in there and multiply by k in the numerator and denominator. When I distribute that multiplication through that subtraction there, it's going to cancel out the k in the denominator. So we're going to get k over p times k minus p. So that's the first thing I'm going to do. And then the second thing I'm going to do is say that through partial fraction decomposition, you guys remember that? Through a partial fraction decomposition, we can simplify this to 1 over p plus 1 over k minus p. Okay, it's a pretty simple partial fraction decomposition. That's why I'm not going through the details, but I just wanted to, name drop that particular technique we learned earlier in the semester, because that is what you can use here to split that into 2 fractions. So now this can be integrated with we can get the integral of that is a logarithm, and the integral of this is also a logarithm. So the benefit is, instead of having a quadratic polynomial in your denominator, now you have linear and linear, right? So that partial fraction decomposition is going to make this much easier to integrate. So now when I integrate it, I get my natural log of the absolute value of p plus the natural log of the absolute value of k minus p. But because that's a minus p right there, if you did a u substitution, I'm going to kind of gloss over the u substitution, but if you did u equals k minus p, your du would be negative dp. And that negative is actually going to show up as a factor in our integrand. So that's going to change that plus to a minus on the left side. On the right side, we just get RT. Yay! Plus constant. We'll throw our plus constant over there. So now we want to solve this for P, right? Yikes. Solve for P? Yes, we can. We can do it. Give me a second to see if I can. Oh, come on. Seriously? There we go. There we go. Okay. Solving this for P is going to be kind of hard. But it's just pre-calculus stuff, it's just logarithms and solving a log equation. So what we're going to do is combine these two guys. Remember that when you have logarithms, if they're added together, you can combine them by multiplying the inputs. But if they're subtracted, you can combine them into a single logarithm where you divide the inputs. So these two combine into log of P over K minus P, like that. And then you do you undo the logarithm by turning this into an exponential. So now we have P over K minus P equals e to the power RT plus C. And remember, we're going to do this thing we've been doing numerous times. That look familiar? Where we split this out into like e to the RT times e to the C. And this combined with the plus or minus kind of turns into that C. So just reminding you, we've done that little two-step thing before. So hopefully that's looking kind of familiar, and we can kind of skip through it. Skip through the deets. Anyway, we got P over K minus P equals this exponential function, right? So now we just got to solve for P. Here's what we're going to do. We're going to multiply both sides by k minus p. Then we're going to distribute, move the p term back over to combine with the other p term, factor out a p, and divide. So here's what it's gonna look like. This is just regular, like, linear equation solving at this point. Move that one back over. Factor your p out. And divide. So p is c k e to the rt divided by 1 plus c e to the rt. And that is what this looks like. That is our solution. Yeah. Cool. So now let's pause. We did all this fancy separable differential equation solving, right? So now let's get into like Desmos or something and just make sure that it works. Let's go make sure it works. What parameters do I have here? I have C, K, and R. C, let's have that equal 1. K, capital K, let's make that equal to like 10 or something, right? So we have like a carrying capacity of 10, right? And then R, I don't know, let's have that equal a half for now and see what happens. Okay. Desmos, if you use the letter R, Desmos is going to interpret that as R, like the R from polar coordinates, but don't worry about it. You can just turn that. See, this is the circle graph of R equals a half if that was R from polar coordinates, but you can just turn that off and just don't worry about it. It's fine. You can still use it like a slider. You know, you can still use it as a parameter like all the other ones. So now we're going to make our P function, P of T equals fractions C K e to the power RT over 1 plus C e to the power RT. Now just type that in exactly as it says right there. All right. And now I should have something which looks like that S curve and has a carrying capacity of 10. It didn't work. I think I messed it up. Oh, thank you. Maybe that's the problem. Ah, thank goodness. Oh, my heart. I was like, oh, crap. It doesn't look right at all. See, it didn't have, I was looking for that carrying capacity of 10, and I do not see that. But there we go. Thank you for fixing that, Cheyenne. All right, there we go. So now it has a carrying capacity of 10. Good. And we should be able to adjust that. If we adjust our carrying capacity, there we go. It adjusts the carrying capacity. If we adjust this rate, it changes how fast the growth happens. There we go. And you can kind of see that. I don't want to make it negative. Negative is, you know, obviously growing, like decaying. I want it to be positive, I think. And then if I change this C value, what you can see is it actually basically changes the initial value. It seems to be essentially changing like this starting point. And I have to shift that up and down, but it's not exactly equal to that starting point. Like if this is it? No, it's not. If C is 0.3, for example, this is 2.308. Right? So that's not the same as the first time we did this, the C value was exactly equal to the the initial value, right? When we did, hang on, gotta wade through my slow computer. I really think something is going wrong with my computer. Like maybe it needs to be updated or or whatever, but it did not used to be this slow. Okay, when we had the original like exponential growth, the C value was exactly equal to the initial value, right? Because when you plug in 0 for t, you get e to the power 0, which is 1, right? So then C equals initial population. But our new version of our population model does not have that property, right? C does not equal the initial population. So maybe what we want to do is try to adjust this formula. I mean, this is a fine formula, I guess, but it would be better if it had the initial population in it as one of the parameters, right? Because then we could actually like very quickly create a formula for a specific population by knowing the initial population, the carrying capacity, and the growth rate, right? Currently, this constant C isn't some easy parameter that relates to something in the real world. So that's what we're going to do next, is try to adjust our formula to work to be more compatible with real world applications. Lecture boards. 9, 23, 1. Okay. CK e to the RT over something else. Okay, I think I can remember that. Here's where we left off. We're solving P prime equals RP times 1 minus P over K. That's our logistic equation. And so far we have P equals C times K times e to the RT over, crap, I forgot. And that's 1 plus C e to the RT. Yeah, that's right. Okay, well, what's P of P0? Our population at time 0, our initial starting population, we can figure it out now based on this. So if I get in here and put in 0 for time, right? I should write this as a P of t. So this is a function of time, right? C k e to the power 0 over 1 plus C e to the power 0. So the e to the power zeros are both just equal to 1, right? That's a 1, and that's a 1. So this is basically gives me the formula. Initial population is CK over 1 plus C, right? Let's solve this for C. If we solve this equation for C, then we will be able to make a substitution in for C and get our formula entirely in terms of parameters that are meaningful, right? It will eliminate the C and put the P0 in there instead. That will be preferable for our intended use. So let's see, I'm going to multiply both sides by 1 plus C. I'm going to distribute this, P0 plus CP0. I'm going to get the C's together on one side, CK minus CP0. Then I'll factor out the C, K minus P0. Then we'll divide. So finally, P0 over K minus P0 equals C. So now I can take that and substitute that expression in for C, wherever I see my C. And I think that'll be a better formula. So let's see, what will that yield? That will yield this. P of t equals P0 over K minus P0 times K times e to the RT all over 1 plus P0 over K minus P0 e to the RT. I mean, I'm not sure I like it better. I'm not sure I like it better. It looks a lot worse right now, right? But at least the parameters involved are all meaningful. We have P0, the initial population, K, the carrying capacity, and R, the growth rate. I mean, yeah, those are all pretty meaningful things we should be able to work with. There is a way to simplify this slightly. If we can simplify the compound fraction by multiplying by K minus P0. So we'll just do that. And there we go. I think we're done. I think we're really finally done. I think that's about as good as it needs to be. Right? That's a good formula. And it's got those three parameters. So now, let's say that let's come up with an example problem. Let's say that a population of squirrels starts at 12 and has a carrying capacity of 100 in its environment. Based on environmental factors. Okay. If the population has grown to, let's say, 30 after 2 days, or let's say years, let's have T be in years, find a function to describe the population over time. Here's our example. Okay. So a couple of things here are oh, I forgot a carriage return in the middle there. That's okay. Find a function to describe. Okay, it's relatively clear what it's saying. What do we know? So starts at 12. So P0 equals 12 squirrels. Okay. Carrying capacity of 100 based on environmental factors. So this is probably something that ecologists would like estimate. They'd be like, you know, study the environment and be like, okay, we think that this environment could sustain up to 100 squirrels or something like that. Or maybe they look at other similar environments and then sort of like make like an infer or something based on that. I don't know. I have no idea how they do this, but we're going to say we know our carrying capacity is 100 squirrels. And so now we don't know the growth rate, but we do have two data points. We have we have our P0 equals 12, and we also know that P of 2 equals 30, right? So after 2 years, our population has grown to 30. So with this extra data point, we should be able to solve for the growth rate. So I'll show you what this is going to look like. We know so far that P of T is going to equal 12 times 100 times e to the RT over 100 minus 12 plus 12 e to the RT. That's this formula with these two parameters plugged in. Okay. So simplifying that up a little bit, we have 1,200 e to the RT divided by 88 plus 12 e to the RT. So that's 100 minus 12 is 88. Okay. Then I know my P of 0 is 12. What if I know P of 2 equals 30? If I do P of 2, I'd have 30. And then I have a 2R over there. And so if I plug in 2 for time, the only unknown in my equation is now the rate R, the growth rate R. So I should be able to solve for R based on that data point. Okay, is this looking familiar? This is pretty familiar to, this is pretty similar to like a lot of application problems you guys have done back in pre-calculus, right? Or like, remember the spring thing where it's like, hey, if it takes this much force or work to like stretch the spring by that amount, then how much would it take to go this far? You use the first piece of information as like data to help you solve for this unknown constant, which is supposed to be, you know, which is constant. Like in the spring example, it was the spring constant, right? In this case, it's like we're using this one extra data point that we have, just one measurement, to go ahead and solve for this rate, which should be constant, according, like for this model, it should be constant, right? And then we can get the function, then we can do stuff with the function, right? So this is a very like, so it should be a very familiar kind of question. Now we have some algebra to do now. So I'm going to get a little more space to do this algebra in. Oops, crap. There we go. Okay, I've got to solve for I've got to solve for R. So I got to do a times, I got to move this over to the other side here. Like that. Got to distribute. Guys, the numbers are getting too big. I don't know what 88 times 30 is. 2640. And 30 times 12, I should be able to do that. 360. There we go. Now I can move my e to the 2r over, right? So I got 2640 equals, I'm going to factor out an e to the 2r, get 1200 minus 360, and divide that. So now my e to the 2r is equal to 2640 over, what's 1200 minus 360? It should be less than 1,000. Oh, guys, I don't know. I mean, 840. Okay, there we go. It's lazy. So 2640 over 840, I guess we'll just drop a 0. 264 over 84, whatever. That's fine. We'll just work with that. I mean, I know we can reduce that further, but we don't need to. So now we'll log both sides, right? To cancel our exponential here. 2r equals log 264 over 84, and then divide by 2. So r equals a half of that. A half log of 264 over 84. So let's see what our growth rate is. A half times the natural log of 264 over 84. about 0.5725. I'm gonna round this to like 0.573. About 0.573. So now our function to describe this squirrel population should now be this, well, what we had over here, this, but with the R plugged in. And now I'm really interested to graph this and just see if it looks right. I'm pretty sure it will. But let's graph it. Let's graph it and see if it looks right. It should have the correct carrying capacity. It should have the correct initial population. And then we can check to see if it passes through the right data point, where after 2 years, it hits, after 2 years, it hits 30 squirrels. Okay, I'm gonna get a completely fresh thing here. I'll call this P of P. I've got 1200 e to the power 0.573 t over 88 plus 12 e to the power 0.573 t. So there is our lovely function. I'm going to compress that y-axis a little bit. Did I do that right? I feel like there's something wrong with it. Oh yeah, 7. There we go. I had a slightly different value, and that had messed up my function. So I just made a typo, but I fixed it. Okay, there we go. So now we can check. Okay, 0.12. That looks good. Carrying capacity of 100. That looks darn good. And now I just need to check to see if P of 2 equals 30. It's pretty close. And it's pretty close. Just the reason it's not exact is because I rounded that R calculation. So I'm sure if we'd been more accurate here, we would have gotten something better. So this was like 2.6. It's even closer now. All right, folks, I think that'll do it for today. It's 12:50. I hope you guys have enjoyed learning about differential equations and the logistic equation in particular. It's a pretty cool application. But yeah, that's it for DEs. Next time I see you will be in a week and a bit. So after spring break, we're going to start studying infinite series, which we're going to then study for like 5 weeks. So see you then.